Hi everyone, and welcome to the Hyperloop seminar. It's actually our last edition today. Just very quickly, if it's your first time or just as a small reminder, so we have two talks today, and after every talk we have a Q&A round. So you can use the button in Zoom. So there is a Q&A button on next to the chat where you can put your questions in. You can also put them in anonymously if you click on that button here. And you can also upvote for other questions if you like a question from someone else, so we know we're gonna answer that question for sure. And yeah, I think that's it with the operations things. So then I would actually jump into the introduction of the first speaker. And yeah, so our first speaker is Giacomo Burani. So he joined Swissloop last season for his semester project. He is a master student at ETH. He's in robotics and control studies. And exactly, so today he's gonna present to us his semester project about the control of the magnetic levitation. And yeah, with that, I think, Giacomo, you can share your screen and we can start with the first presentation.
Hi everyone, thank you all for joining. Today I would like to present you my semester project on the development of a magnetic levitating system for the Swissloop pod. The motivation behind this project is that greenhouse gas emissions have been identified as one of the main factors behind climate change, which could have drastic effects on the world in the next years. It is therefore our duty to try to minimize this effect by moving towards the decarbonization. This is a very long process that could start by reducing our emission by adopting the most energy efficient solution in all energy factors. Today, I would like to talk to you about the transport sector, which accounts for 16.2% of the total greenhouse gas emission. For the percentage listed here, it seems like rail is the most efficient choice at the moment. This, however, could be due to different penetration of the technology in the sector. Therefore, an energy consumption unit is introduced to make a fair comparison, and it's calculated as megajoule per passenger per kilometer. In this table, this quantity, together with other parameters, is presented for various methods of transports. As you can see, train and buses have the lowest energy consumption at full capacity on the third column. But when this quantity is adjusted with the statistical occupancy, buses seems to be more energy efficient. However, they still present some problems such as speed limitation, low capacity, and traffic problems. Another transport method is visible on the table, which is the Hyperloop concept, which can be a valid alternative to this classic method of transportation, and even better. This technology consists of magnetically levitated capsules traveling in vacuum tubes. It can reach a theoretical top speed of 1000 km per hour, which is comparable to that of planes and trains. It has a theoretical energy consumption comparable to that of train and buses, as you have seen from the last table, and it is designed to not interfere with other capsules, solving the traffic problems. And it's quieter than both planes and train, as the tubes can be placed underground or be soundproof. It seemed like this technology is combining the speed of planes and the energy efficiency of trains, and also bringing some additional advantages. Since this concept gained traction, a lot of university teams and companies were founded to develop this technology. One of them is the Swissloop team, founded at ETH in 2017, which I joined last season. This team builds a scaled-down prototype following the Hyperloop concept, the so-called pod. It innovates it and improves it every year and tests it on a rail track. Until last year, the pod consisted of a cart with wheels traveling on rail. One of the goals for last season was to remove the wheels, which are source of friction and speed limitation, and provide a new guidance system to keep the pod centered on the track, because the new propulsion motor concept doesn't allow for passive stabilization anymore. My contribution to the team has therefore been to develop and simulate an actively controlled vertical levitation system and a magnetic guidance to solve these problems. Here, you can see a 3D model of the pod on the left and a cross-section on the right that better presents the components that are part of this project. The guidance wheels are removed and substituted with safety wheels that works as hard stop to prevent derailment and excessive displacement. The lateral guidance system consists of EMS, electromagnetic suspensions, and has to keep the pod centered with respect to the center line. This is important because the reluctance motor, as I mentioned earlier, in the center introduces strong disturbance forces when it's not perfectly centered. Finally, the vertical levitation is achieved using HEMS, hybrid electromagnetic suspension. This consists of electromagnets coupled with permanent magnets. The choice of using permanent magnets is made to compensate the constant weight of the pod and be more energy efficient. Before introducing the dynamics of the system, I would like to introduce some key parameters that allow to simplify the modeling and the simulations. The first one is the current rise time, which quantifies how fast the current is able to react and change. The dynamics time constant is similar and it determines how fast the pod moves. It is calculated with a freefall approach and it's the time it takes the pod to reach the maximal displacement allowed. Comparing these two quantities, as shown in this table, allows us to assume that the currents change much faster than the pod moves. It is therefore possible to control each electromagnets and hybrid electromagnets independently as 1 degree of freedom systems. This allows us to reduce the complexity of the dynamics and to avoid using a MIMO controller, for example. In this slide, you can see the control structure I choose for this system. It is a cascaded PID controller. I choose it because it allows us to control two quantities together that change at different rates. According to the time constant we just saw, the faster changing variable is the current, which will be controlled in the inner loop, while the position of the pod will be controlled in the outer loop. This control loop is then simulated in Simulink. This control structure allows us to simplify the dynamics of the electromagnetic circuit. Being inside the inner loop, we can therefore assume that all the quantities related to the outer loop are constant. For example, this change in the air gap that you can see here. This simplifies the dynamics a lot and allows us to calculate the transfer function from the voltage to the current. This is important because the inverter the team uses acts on the voltage and not on the current. Now let's talk about the physical dynamics of the vertical levitation system. In the sketch, you can see the model chosen for this system and the force involved. As already mentioned, the vertical levitation system is made of an electromagnet coupled with permanent magnets. Ideally, the permanent magnets should compensate the weight of the pod, and the electromagnetic part should only handle the inertia and the changes in reference. Here you can see the equation I used to express the dynamics of the vertical levitation system. The strategy I used is to simulate each hybrid electromagnets independently. And as already mentioned, safety wheels are used to limit the displacement of the pod, which has to stay in the range of 7 to 14 millimeter with respect to the rail. In the case of the lateral guidance system, disturbance force is not constant anymore, but is a function of the misalignment of the motor with respect to the center line. It is very strong, therefore to be able to control the pod, the allowed displacement range is smaller. Given that it's only possible to attract with electromagnets, I need one electromagnet on the right and one on the left, front and back. So a total of 4 electromagnets for the lateral guidance. The strategy is to divide the electromagnets in couples, front and back, and to operate only one of the electromagnets, left and right, depending on the direction of the disturbance force, which can be both positive and negative depending on the misalignment. Disturbance force has been extensively analyzed due to its importance. In this graph, only the negative part is shown, but the positive part is specular. The equilibrium position for the lateral guidance was chosen to be 5 mm, and as you can see, the bigger the displacement with respect to the equilibrium position, the bigger the absolute value of the disturbance. You can also see the ripples in the force, this oscillation that you can see in the graph, which are caused by the misalignment of the motor coils with the track teeth while moving. For simulation purposes and to be safe and conservative, we choose to only consider the biggest disturbance force for each air gap. Another important parameter to take into account was the traveling speed, because it both influences the propulsion force and the generated levitation force. As you can see, when the speed is 0 on the left side, the magnetic loop closes nicely and the generated force is maximal. While as the speed increases on the right side, the magnetic loop seems to be dragged along the rails as it takes time to magnetize the metal of the rail. The longer the magnetic loop, the bigger the loss in the generated force. Also, the orientation of the electromagnets matters, but we will see that on the next slide. Matter of fact, 2 possible orientations were investigated, the parallel and the perpendicular orientation. But after further investigation, we opted for the parallel. So for this configuration, as it presented a smaller decrease in the generated force between the still position and the top speed. So, for example, you can see in this on the left side, this graph is for the perpendicular orientation, and you can see that between the 0 meter per second and the top speed at 20 meter per second, the drop in the generated force was 1100 Newton. While on this side, with the parallel orientation, the drop was maximally 2000 Newton in this case. These 2 lines represent the generated force at 20 amps. One in the case of 0 meters per second and the other one for top speed. In the early stages of the project, the force generated by the electromagnets was modeled in the following manner. But then to obtain more realistic simulation and be more computationally efficient, we decided to substitute the model with lookup tables filled with data coming from ANSYS simulation. The inputs to this table were the current, the speed, and the air gap, and the output was the generated force. Here you can see an example of these tables for the specific for a specific traveling speed. The strength of the permanent magnets was chosen to be such that when the current was at -20 amps here on this axis, the generated force was close to zero. This allowed the pod to recover when it got too close to the rail. Oh, sorry. In the case of the lateral guidance, the generated force was maximal when the current is maximal and zero when the current is zero. And as already mentioned, the sign of the disturbance force determines which ends, left or right, is active. An important assumption here is that there is an instantaneous switch on and off between the left and the right ends. The system was tested for reference tracking, lateral and vertical acceleration, and power consumption. And to test the system, the reference was changed to simulate bumps and disturbances in the track, and noise was added to the feedback sensor. Here are some results for the lateral reference tracking. As you can see, the system is able to track the reference nicely and the safety wheels are never engaged. The total consumption of power was in this case estimated to be 124 watts. Sorry. In the case where noise was added to the feedback sensor, we can see that the guidance is still able to follow the reference, but safety wheels are minimally engaged in these cases here. As expected, the power consumption is increased to 187 to counteract the noise effects. The results for the vertical levitation system are similar, but as the allowed levitation range is bigger and the disturbance force is smaller, the safety wheels are not engaged, even in the case of noise corruption. In conclusion, the system is able to efficiently track the reference, but in the case where noise is added to the system, the safety wheels need to be minimally engaged, as we see. Sometimes we noticed huge spike in the accelerations, which you can, for example, see here. You can also get some spikes at minus 30 meter per second squared. But as these acceleration were instantaneous, there was no concern because they had negligible effect on the speed. The noise increased the power consumption by 50% in the simulations, but this has to be further investigated in the physical system because this project, in this project, the current was able to change really fast, which may not be the case in the reality. And after, as a like a bigger conclusion, I suggested to increase the operating range for the lateral guidance to avoid the need of safety wheels engagement. That's all. Thank you all for the attention. Do you have any questions?
Yeah, thank you, Giacomo. So actually, we do have a few questions in the Q&A, and I think we're just gonna start with them. So one of the questions is particularly about the HEMS, so the vertical system. So you mentioned the magnets are compensating for the weight of the pod. How accurate is this calculated, and can you still load different kind of weights on the pod, or is it specifically for one weight?
So the last year the competition was without any payload. So the weight of the pod was pretty much known, and we also added a safety factor, and we calculated it by summing the individual force of the electromagnets. Sorry, of the permanent magnets to compensate just the weight of the pod.
Okay, but in the end, it was an assumption from the mechanical designs, from the materials, which
Yeah, exactly.
still have some. Okay, but you calculated it that it lifts more, like the upper weight of the paw, or
Well, you still have also the force coming from the electromagnets. So the baseline was to be able to levitate at the equilibrium position only with the permanent magnets, and then to handle the disturbances and the bumps in the track, or like any other external disturbance, to use the force coming from the electromagnet and not the one coming from the permanent magnets.
okay, so that in the end you don't need additional current energy from.
Yeah, exactly. If
Yeah.
everything went smoothly and the track were perfectly aligned, only the permanent magnets would suffice.
Okay, nice. And I saw Czech is raising his hand. You want to pose a question right now?
Yeah, if that's possible.
Yeah, sure.
Thank you for the presentation. I have a couple questions. So, if, to my understanding, HEMS works by kind of running the magnetic field in the coils the opposite direction of permanent magnets, correct? In the case it wants to weaken the magnetic pole force. That's how it
Sorry,
works.
can you repeat?
Oh, yeah, I'm just clarifying. So, it is the way that HEMS controls the magnetic pole force? Is it by running the direction of the current in the coil, the
Exactly.
opposite direction of the field in the permanent magnet?
Exactly.
So,
Basically, with the positive current was defined that it strengthens the force coming from the electromagnets, while with a negative current, it weakens it. And
okay.
so here, yes, here. This is, maybe I wasn't clear enough. This is the graph of the generated force as a function of the current and the air gap. And as you can see that when the current is maximal, so 20 amps, the generated force was maximal. But when the current is negative and maximally negative, the generated force was 0.
Oh, okay, yeah. Okay, I understand. And a follow-up to that is, did you guys consider potential demagnetization in the calculations and maybe like Kansas or something? If you're
Um,
running current in the opposite direction of the permanent magnets.
yeah, I know what you mean, but no, we didn't account for that. But the physical system was built. I wasn't there anymore because I was doing my internship, but it worked smoothly. Like the levitation was working fine.
Oh, okay. So it seems like that's not really a concern. And last question is, um, how were you guys counting for changes in inductance, or is it kind of negligible and it lined up with your assumption?
Changing in inductance, where?
Oh, like the inductance of your hems, for example, would change as a function of the gap, right?
Oh yeah, sure. It was all in the so first here in the model you can see it's accounted for in the maybe I have an equation somewhere. No, I don't have the equation with the inductance, but when you simplify it, you can kind of get something like this, which already accounts for the air gap and the current flowing in the electromagnet.
Okay, thank you. And um, so in terms of designing the vertical levitation system, you design it around the weight, right? I assume. And
Yep.
so how do you design the operating point for lateral guidance? Just curious.
The operating point for the lateral guidance, yes. So, okay. So basically, there was another engineer which was responsible for the design of the motor. And long story short, he gave me this 5mm as a reference for the equilibrium position. And we designed everything coming from that. But I think it was coming, like it was a bit of a trade-off between the like if you allow too much of a displacement, this disturbance force get huge. So you kind of want to minimize that, but you also have other constraints like structural constraints and other components. Like the levitation was not the only components of the pod. So this was basically given to me by the motor engineer. And the range, the operation range for the lateral guidance was chosen to be like not to have too big of disturbance forces.
Awesome.
Thank you
Yeah,
for your
and
questions.
yeah, thank you.
Okay, nice. Thanks, Jack, for the questions. And maybe one last question. So you mentioned you weren't there when they tested the pod, but maybe did you get any feedback on your designs? Like, is there anything you would maybe change for future control designs?
So I talked with the guy who continued and assisted me during my semester project, and like he told me like everything worked smoothly, and I looked to the schematics of the levitation, and basically the cascaded PID structure remained.
Mhm.
And it worked fine. Maybe some improvements could be made on the noise rejection or estimation of the position, like with some statistical method like Kalman filters, but I think they used it.
Okay.
But yeah.
So it's more like additional things on top of your controller.
Yeah, I mean, it's a simple PID controller. I don't think I'm not saying it's the best control structure, but it was simple enough to get started.
Yeah.
It was never done before on the Swiss Loop team, so it's a nice point to start.
Okay, nice. Okay, I think that's a good ending of the question round. Thanks a lot, Giacomo,
Thank you
for
all.
your presentation. And then I would give the word to Gabriele, who is gonna introduce us to the next presentation.
Yes, thank you very much. I'll just quickly introduce the next speaker. Oliver has been in the TUM Hyperloop team for 4 years now, I think, for quite a long time since we started developing our full-scale Hyperloop demonstrator, which in principle is a 4-ton pod in passenger size. And yes, I think it will show an image anyway right now. And his task has been from the beginning to work on the control for this set magnetic levitation system, and in principle quite similar to what we've just heard. And he will go in particular into the use of equivalent magnet circuits for modeling the levitation system for the control. And so I'll just hand over to Oliver for this.
Yes. Hey, everybody. Nice to see you guys. And yeah, thank you, Gabi, for the introduction. I'm Oliver, and I work, as Gabi said, on the TUM Hyperloop and on the levitation modeling and control. So it actually fits very well to Giacomo's presentation. Yeah, let's get started. So on this slide, you can see our current demonstrator setup. It's on the left side, you can see the TUM Hyperloop pod. It consists of a passenger module, which you can see on the top, where the passengers can sit in quite comfortably and the drive in our demonstrator, and on the bottom, like sitting right on this trailer we have, is the so-called service module. And in this service module, all the electronics of our pod sits. There's the propulsion hosted, and there are also the electromagnets for guidance and levitation. And on the right side, you can see the tube of our demonstrator, where we have like the two L-shaped guideway elements. So on these Ls, there are the reaction rails for levitation and guidance, where we pull ourselves up to. The tube is currently 24 meters long, and it's also possible to evacuate it and to test the demonstrator in a real vacuum Hyperloop environment. I will now talk a little bit in more detail about the magnet system, and especially how it's important to model it correctly and in quite a detail to have a useful tool for simulations, for vehicle simulations, and also for model-based control algorithms. So the general goals of every model are, I think, to have a model that is intuitive and probably adaptive for different scenarios or different geometries. And there's this general conflict of interest that it should always be as simple as possible, but at the same time as complex as necessary to cover all the relevant dynamics or static characteristics of the system. Regarding the levitation systems, there are different methods how to gain model knowledge. I think the most common one is the finite element approach. It's very, it's kind of straightforward, and you can derive a lot of deep characteristics or like very easy characteristics about your levitation system. Sometimes it can be very challenging and computationally intensive, especially when it comes to transient simulations. I really liked your simulations about the speed of the pod regarding that, so congrats to that. Another disadvantage can be that the FEM results are maybe unusable for model-based control applications. Another method is an electric circuit model. I think this is kind of the thing we just saw in the previous presentation. Another approach I want to focus on today is the so-called equivalent magnet circuit. So as you probably know, you can kind of all electric circuits, you can also replace or like also describe using a magnetic circuit. And yeah, this presentation will be about that. So let's have a quick roundup about the influences of the static and dynamic behavior of a levitation system, or also guidance system. It doesn't really matter at this point. So the main influence is obviously the air gap between the reaction rail and the pole surface of your electromagnet. Then when you consider these equivalent magnetic circuits or also finite element models, it's always important to kind of analyze your flux lines and also consider their length and diffusion or possible leakage flux paths. So these are the geometry influences. Then we also have, of course, material influences, which are especially the permeability of iron and the variation due to saturation. As we all know, we all try to make the pods as light as possible. It's a common choice to have or to operate a levitation system in an area where the saturation effects of the iron already come into play. So it's just like another conflict of interest to have it lightweight, but also to maybe avoid or like don't go too far into saturation. But it's definitely a thing you have to consider in the model. Then another thing is the hysteresis behavior of the iron. And of course, possible eddy currents, we already heard it in the previous presentation, can have an influence on the buildup of your magnetic fields. Okay, let's have a quick look about the equivalence of the electric circuit to the magnetic circuit. So we also have a potential quantity. So the voltage is replaced by the magnetic supply voltage, which is also called magnetomotive force. And instead of a current flowing through an electric circuit, we now consider the magnetic fluxes going through the magnetic circuit. We can model resistances similar to the electric circuit by magnetic reluctances. And we can also model inductive behavior by magnetic inductances that can be used to describe eddy current influences. Then in analogy to Ohm's law, we can also just formulate Hopkinson's law as a founding for the magnetic circuit. So the magnetic supply voltage equals the magnetic reluctances times the fluxes going through the elements. For a single or simple solenoid, we can also formulate Ampere's law. So the magnetic supply voltage coming from the solenoid will be the winding number times the current. And then for building up these magnetic circuits, you can also use Kirchhoff's law like you are used to in electrical circuit. Very important design steps for the equivalent magnetic circuit are that you have to, before you can start, you kind of have to identify your flux paths. So either you know where your flux is going, where your acting flux that actually building up the magnetic force is going, or where possible leakage fluxes are going, which you kind of want to avoid, but you have to know where they are. So it's all like sometimes also useful to start with FEM analysis to identify these flux paths and lengths, and then continue doing the equivalent magnet circuit. Then you have to see what your assembly looks like and have to model the geometry and different components by lumped elements using these magnetic reluctances or inductances. And at that point, I think it's important to use simplifications so you see which elements you can combine or omit, which are not that important. Then it's really good to have a lot of insight in your material characteristics. So if you know some BH characteristics or curves, it's always beneficial. And at that point, when you kind of identified all the previous steps, you're able to formulate your circuit equations. And it's quite rewarding since your outputs can be the current as well as the magnetic force, which will both be functions of the magnetic fluxes you are modeling. These elements I showed you before, they can be extension, or there are some tools to quantify them for different materials or different geometries. So the magnetic reluctances will be based on the length of the component. So this is why you must need to know the length of your flux lines, and also the mu r and the surface area or the area A of the component. And the mu r can either be constant when the element is air or vacuum, or you can for the iron components you should use the saturation behavior. So for this you can either use BH curves from ANSYS or whatever, or I took this ansatz from literature where they use these alpha values to describe the age of B curve, so not BH how we are used to it. And with this way, you kind of can translate your saturation into the flux description, which you use in the equivalent magnetic circuit. Then you can also model magnetic inductances, as I said. These will deaccelerate or slow down your buildup of the magnetic fluxes. And the equation is similar to how the inductance would be in an electric circuit. Then you also kind of have to connect your equivalent magnetic circuit to an electric circuit to generate the input-output structure, because similar to the previous presentation, the input will be our voltage and our outputs will be based on the fluxes. So you need these also an electric circuit, which you can then put in the equivalent magnetic circuit to generate this structure. I will just show a quick example of how you do it. So if you would, this is just a one iron element or like one element magnetic circuit you are describing here. So your magnetomotive force is the flux times the magnetic reluctance, and it also equals the magnetic supply voltage, and is deaccelerated, or like there's also a voltage or magnetic voltage dropping at the inductive element. Then you can formulate your electric circuit, which is in this case is a simple LR circuit with the well-known equation, and the induced electric voltage here can now be also formulated in terms of phi. So the change of your flux times the winding number is your induced electric voltage. And when you plug in those two equations, you will come up with the actually coupling. So where you have your input, your supply voltage, and your outputs will be based on the fluxes. So this will be the goal at the end. We have a homopolar system in our demonstrator, which I think you called it the parallel configuration. So it's actually the same. So we don't have a change in magnetic field direction over the length of the pot. And so we identified the different components of our magnetic system. So we have a reaction rail at the top, and then we have a solenoid with a core in the middle, isolation foils, and two limbs on the side that guide the acting flux to where we want to have it. And of course, we have to consider different leakage flux paths. And then we came up with a model structure based on all these steps I've showed you previously, and to generate a very nice model. You will at some point have probably unknown parameters, which can be the geometry. So you maybe have to combine some elements or make assumptions on where special leakage fluxes are going kind of in average. There will also be possibly material behavior characteristics which you don't know. So you don't know the BH curves of all materials. And also it's very hard to quantify the eddy currents. So this is the reason why it makes sense to let these parameters open and kind of to fit them or to compare them to measurement data or also finite element data. We use this on the right side. You can see our Levitation test stand, where we are able to get a lot of measurements, like the force or current measurements, and compare them to the model output and kind of fit the model to the actual system. And for this, we use nonlinear optimization tools that are able to find a good solution for that. Okay, let's have a quick look at our results. So the static considerations are done by the current air gap force relationship. You can see here normalized force values over normalized current values at different air gaps. So our nominal air gap is 10 millimeters. So I showed like the measurements are in the green and the model is the dotted red plot. And you can see how well we can fit our model to do or to map perfectly the actual behavior of the real system. The dynamics of the system you can, for example, analyze by using like differential inductance. Now I'm talking about electric inductance again. So we considered here or investigated current responses on different voltage inputs. And you can see again, so the inductance, we also heard it in the previous talk that it changes with air gap and also current. So with higher currents, we have lower inductance due to the saturation. And also like the other way with lower air gap, the inductance increases because you have more material close to your core or more iron material. Yes, and let's continue. So what are the applications of our equivalent magnetic circuit? At first, you have a very powerful and easy levitation simulation tool where you can simulate your different control algorithms. Then you have a big advantage because you modeled one single part of your whole pod very well and accurately. It's easy to implement this very well model into bigger vehicle simulations where you have like several electromagnets also for levitation and guidance. You can obviously use it for both. And another big plus is, of course, you can derive model-based control algorithms on this because you have like mathematical equations that describe your model, which is a very nice tool. And another interesting aspect is that you are also able to like long-term to design your system. Like similar to FEM, you can gain knowledge. What happens if I change this geometry? What happens if I use that and that material? And you can kind of tweak your system and see what happens before you design it. Then as a quick motivation, I brought this video which shows our first Hyperloop test in vacuum. You can also see it on YouTube. At some point, our levitation system is also in work. And yeah, I just want to show it as a motivation since the equivalent magnetic circuit is also one part of this happening, yes. Yeah, this is our pod interior. Maybe you've seen it somewhere on social media. Yeah, I think that's pretty much it. Here are some very nice references I have for you guys regarding this subject. And yeah, thank you for your time and feel free to ask questions.
Thank you very much, Olli, for the presentation. We have one question from the Q&A function so the question is about the leakage flux The question is in particular, what would happen if you don't account for it, and why is there a leakage flux at all?
Okay, yeah. So let's maybe go back. So there, of course, the goal should be that there's no leakage fluxes going through the air here at all. So you can only have the acting flux that produces your force, but you will always have some leakage fluxes, especially with wider air gaps, when like the difference between the magnetic reluctance of the air here and added to here is like close, similar to this distance here, and at that point the magnetic flux lines will also go through here and not like choose this desired path here. You can also model it without. Then you just have like fewer states. It's also possible, but I think it's like more like closer to reality if you also try to somehow compensate this influence. But of course, it's also possible to start with only the acting flux and see where you get there. Yeah.
Okay, then we have two raised hands from Giacomo.
Yeah, thank you for the presentation. This is actually really cool stuff. So, yeah, so where do you see the model kind of falling short? I can see that the reluctance isn't really the same as resistance in the sense that it's not like dissipating power, right? The same way resistance would dissipate in electrical. So like where else do you see the model falling short?
I mean, you can always try to make things more complicated. So you could at some point maybe add something like what Giacomo did, that you have like also have a distributed parameter system. So when you go over unmagnetized rail and see what happens then. Also, we didn't include thermal stuff yet, so heating up of the coils. But like in general, it sometimes is very complicated with the or like not as intuitive as it seems, because you have these saturation curves. For example, if you use this ansatz, and they will go to in every of your magnetic reluctances, and then you will end up having like very huge nonlinear equations that are not that intuitive. So this can be a drawback compared to other systems, but of course, on the other hand, you don't have to look in these equations all the time. You just let Simulink do it and solve it, and just look at the output and see if that makes sense. Yeah.
Gotcha. Yeah, that was basically my follow-up question. But do you have any more comments about using equivalent magnet circuit and FEM, for example, hand in hand? Is the circuit kind of a way to help you design, give you the groundwork for the intuition behind designing things like this, and then FEM gives you the actual numbers? Is that how that pipeline works?
Yeah, I guess that can work. And also, I'm not sure if FEM is capable of giving you, I mean, it solves all the same equations we also formulate here, but you don't have a magnetic representation of your outcome. So I think that's an advantage of this modeling technique, that you actually have a function of the magnetic force based on current and air gap, or of your inductance. And I'm not sure, maybe it's also possible with FEM, but I don't know for sure.
I see. Last thing is just where can I like find more resources for this kind of stuff? Or are these in the end I can look at in the slides?
Yeah, I think like a lot of stuff is in Transactions on Magnetics. I think it's a journal, and yeah, there are different groups that publish their results, and a lot of times they also compared them to the finite element method, or like simulations they did, and yeah, were able to achieve really nice representations of their model.
Thank you very much.
Sure.
Okay, and one more raised hand from Giacomo.
Hi, Oliver. Thanks for the presentation. I just wanted to ask you whether, why it seems to me like in your model, the only changing parameters are the air gap and the current to get the output of the generated force.
Yes.
Is there a reason why you didn't account it for the traveling speed? You didn't find any difference?
We just didn't do it yet. We are
Okay.
planning on doing it, so that's why I liked your simulations based on the the magnetic force based on the speed. So we are also planning on doing that and to extend the model with this aspect. Yeah.
All right. Thanks.
Sure.
Okay, then I think we have no more question to the topic. Thank you very much, Oliver, again for the presentation.
Sure. Thank you, guys.
Somebody willing to give some final words? Andrea, I think.
Yes. Just really quick, some words. Gonna have some slides. So thanks everyone for joining, and thanks Giacomo and Oliver for your presentation. And just as a reminder, so you can always look into our past talks on YouTube. We have all of our talks there uploaded. And so this has been like the last typical Hyperloop seminar for this semester, but we're actually going to have a special session next week on Monday from 6 p.m. to 8 p.m., which is mainly for EHW teams, but it's it's a bit like the economics and the management of those Hyperloop student teams. So maybe it's also something interesting for you in there. We will definitely post something on LinkedIn. And there will also be another talk in January. It will be on the 8th of January. But yeah, we will keep you posted on that one, and we will also give you more information next week. And yeah, with that, I think we're at the end of this seminar. And thanks everyone for joining, and have a nice evening.